Hello everyone, I am Karthike and today I am excited to present our work on reversible vision transformers. Let's start with a review of the reversible transform. The reversible transform is a simple invertible operator composed of functions f and g that do not necessarily need to be invertible themselves. The inputs of the transformation can be calculated exactly from the outputs through a single query of each f and g. Now let's briefly review the process of activation caching in vanilla transformers. The input I is processed through the first n-3 blocks of the transformer to yield the internal representation Vn-3. The activation is cached and then processed through block n-2 to yield Vn-2, cached again, and so on and so forth until the end of the forward pass. Backward pass begins with the calculation of gradient at Vn using the cached activation features. The gradient is propagated to the previous layer where the cached activations Vn-1 are used to calculate the gradients at block n-1. The process of using the cached activations to propagate gradients is repeated all the way to the input block. Now consider the forward pass of our proposed memory efficient vision transformer. Similar to the vanilla case, consider the representations once propagated to Vn-3. The representations at block n-2 are first calculated from Vn-3, after which Vn-3 is discarded. This is in contrast to the vanilla case where Vn-3 is cached. This process is then repeated till the output is obtained. Now consider the backward pass. At this stage, the GP memory consists of no internal activations, which is a massive saving over the vanilla case that caches all the internal activations. Now starting from the output, the representation Vn is used to calculate the input to the reversible block n in an analytic fashion. This yields us V hat n-1. This recalculated activation is then used along with the gradient at the end of layer n to calculate the gradient at the end of block n-1. This forms the central mechanism for gradient propagation without activation caching in reversible vision transformers. This representation Vn is then discarded and the process is repeated to first estimate the activations at V hat n-2 and then propagate the gradients to the block n-2 and so on and so forth until the input layer. We build up the vision transform architecture in this reversible mechanism to reap the memory benefits of reversible training. In particular, we subsume F to be the attention and G to be the MLP block and reconfigure residual connections to allow reversibility as shown. This decouples the reversible transformer training memory from the number of blocks in the architecture, allowing, for example, a 100-block model to train on the same hardware infrastructure as a 2-layer model. By nature, feature dimension changes hinder reversibility. In our work, we use the simple technique to sidestep this challenge and propose reversible hierarchical vision transformers that can still reap the training memory benefits. In interest of time, I suggest the interested reader to please refer to the paper for further architectural details. This completes the brief overview of the technical foundations of the reversible vision transformers and brings up three natural questions in the minds of any interested practitioner. First is the performance question, second, the efficiency question, and third, the speed question. We now conclusively answer all three of them. The answer to whether this structure causes the network to lose capacity in any way we find to be a resounding no, specifically across two model designs, three model sizes, both image and video modalities, and across three well-benchmarked visual recognition tasks such as image classification, activity recognition, and object detection, and at matched flops, parameters, and activation sizes, we find the reversible networks to match performance exactly of vanilla networks on both accuracy and AP. On the efficiency question, we find the memory gains to be massive. On ImageNet, vision transformers enjoy up till 15.5x lesser memory footprint, and AMVID models up till 4.5x smaller footprint. Similar story is repeated on action classification, where we can go up till 3.5x higher in batch size. Note that this is particularly useful since video is the most memory-starved regime of visual recognition. We also find a similar story to hold on object detection, where we see matched accuracies at 57% of the per image memory cost. Finally, on the training speed, we find reversible models to easily overcome the burden of additional computation through increased parallelism with a larger batch size. In fact, reversible models can go up till 2.1 to 2.3x faster in training throughput on a V100 for sufficiently deep models and up till 4x higher training throughput on a A100 compared to corresponding vanilla models. For further details on trained models, ablations, and much more, please talk to us in the poster session or scan the QR code below.